Good morning.
You're listening to Classic Hits 102.7 The Try.
How is everyone today?
You're back in Oregon.
I'm in Oregon. I'm back at my desk. We had a good drive home. Now it's time to heal up. I got this huge gash out of my leg from crashing. I crashed more than anybody. Well, you guys are here on time. I want to share a drawing that I did a number of years ago that was one of the craziest additions I ever drew on somebody's house. This gal in Ashland was just super creative, but one of the things that was I've never drawn before was this. She wanted this circular kind of a turret. So it's like you've seen those in castles and so forth, but not only did she want the room to be circular, but she wanted the rafters of it to be curved. And so that line up there having a curve to it, kind of a circular curve. And so it's just a really kind of a cool shape. And so this was just curves and crazy shapes, unlike kind of anything I'd ever drawn before. But in a sense, that's exactly what we're tackling today. Things that have kind of rotational sort of a shape to them. So let's start off with that. Goodbye, Mas Caratolo. So we got a number of sort of neat things that I want to show you before we're all done today. Let's see, is this thing speaking? So you've probably heard of the formula for the volume of a cone, and I'm going to show you why that volume works the way it does today. Let's see. Uh-oh, we're playing the lag behind game today. That's not good. Let's see. We're connected there. That is good. Let's see what the iPad thinks we are hooked to. The iPad is hooked to the slow network. That will help. Let's try that one more time. Apologize. So while we are waiting for this, just to keep it really simple, let's to model that roof that I just showed you, let's consider the really simple parabola y equals x squared. And let's rotate that around the x-axis. So I'd like you to kind of just sketch that on your paper. Think of y equals x squared, the parabola. So we're going to treat that curve on that building that I just showed you as being like a parabola. And I'm actually only picking a parabola because it turns out to be a lot simpler than a circle. Wow, why is this thing just not working? Let's turn off all extraneous stuff here. And try one more time. And let's do this from, let's consider the parabola to go from, say, 0 to 2. I don't know. So we are, that's incorrect. So if we consider this thing as being rotated around the x-axis, the question is, do you see kind of that roof that I just drew a second ago? And you said that you'd have a cone, except for that it's got a curve in it. This is similar to what we did yesterday. And I also rotated yesterday around the x-axis. Maybe we'll go back and rotate this around the y-axis too. The way you want to think of this as slices. And so we need to be really careful with this. And I wasn't super careful about some things that I did yesterday, and I want to be a little more careful today. So for instance, if I just pick one random spot to kind of make my slice right here, I'm taking a slice out of this. And so remember, what you're really doing with an integral is adding up infinitely many things. And so does it make sense that that slice that we're taking in this is really a cylinder? A cylinder's volume is pi times radius squared times height. So when we spin something around an axis, it's going to make it round, and therefore when you take a slice of it, the volumes that you're going to get are cylinders. So I like to think of this thing as just a stack of cylinders. Do you see it that way? Let me draw it a little more carefully, because again, I'm most interested that you are making sense of this. So does that look better, being a 3D drawing? So really then what we have to determine is what is the radius and what is the height? What is that? So there's my height right there. That's the height of it. And if I look over in this picture right here, where that cylinder is, and I guess maybe I'll draw the rest of it, spun around. So this is a complete side view, so I'm not really drawing it three-dimensional. To get to our spot, aren't we going over X and then up Y?
Could I ask a question?
Yeah, go ahead.
Wouldn't it be made up of cylinders that have the sides angled?
Nice job. Everybody understand that point? Aren't these Aren't these sides angled? So is that really a cylinder? And that's kind of what she's, I think that was Alicia that said that. Are those really cylinders?
You know, I'm thinking about that too, and I think it is still a cylinder because we're adding our y equation, which kind of takes into account those edges, and because they're infinitely small, like we did with rectangles, then they're kind of hitting kind of level, if you know what I mean.
Yeah, the answer is they're only cylinders if they're infinitely small. In other words, h is on its way to 0. So in a sense, they're not cylinders if h is 0.1. They really are at an angle. But if they get infinitely short, does it make sense that you could think of them as cylinders? Remember that height is literally going to 0 here. And so because of that, we can consider them cylinders. But you're exactly right, Alicia. If they are a slice of any thickness, then they're not cylinders. They're truncated cones. And so that's a very good point you're making. So thank you for thinking about that. Notice over here, my drawing, like I drew it horizontal, my little blue line, I drew it horizontal, but is it really horizontal? Not really. So yes, keep asking those questions. So then in this picture over here, my height is really a little bit of x since it's horizontal. And my radius, which is from here to here, is really the same as the y coordinate of whatever point I pick. And so dx is going to stay the same every place I go, but notice I'm getting different radiuses all the time. And that's what makes calculus so powerful, because the radius is changing. If you go to a different location, then your radius is shorter. And so you end up adding up the volume of all these cylinders. And that's what integrals do. They add up infinitely many infinitely small things without you having to add them up. That's the larger issue. And what's cool about what we're studying now is it isn't just have to be rectangles. Like integrals add up infinitely many infinitely small anythings, not just rectangles. And so we're actually adding cylinders this time in most of our problems, really all of our problems today. And so we're going to sort of let all of this happen while x kind of stays between 2 and 0. That was just the choice I made. So notice my x coordinate right here. I'm going to let that x be anything, well, everything, not just anything, but everything between 0 and 2. And wherever x is chosen to be, then I'm going to get a different y, a different radius every time, and then dx will stay the same every time. And so then what I'm really doing is saying, okay, then what's my integral, or what am I adding up? Well, it's pi times radius squared, but my radius is y, and my thickness is dx. The question is, do you see that statement as just pi r squared h still? It's just that I'm sticking that into the language of x's and y's. So this is the hard part of these problems. Now, as I said a little bit yesterday, this isn't going to work because we have x's and y's in the same problem. And you understand that, I hope, from the time we spent with substitution. So I've either got to get dx to turn into dy, or I've got to turn y into x. And so they're all x's, and then I can kind of get on my way. And as I said the other day, it's usually easier to switch out y. How am I going to switch out y?
Plug in y's equation.
Yeah, I have this equation up here that tells me the relationship between x and y that creates that red curve. So since y is the same as x squared, then I can replace y with x squared, and then I can work all in x's. So now I can say, oh great, since I know that it's from x is 2 to 0, then I can let x be 2 and 0. And pi is in here, and y is being squared, but I just replaced y with x squared. And so now I can actually answer this question. And notice this particular integral is really easy to take. So I'll go ahead and do it and not cheat. Again, I'm welcome to pull any constants out front. So I say, okay, that's a simple integral because the integral of x to the fourth is x to the fifth over 5 according to the power rule. And then I can evaluate it at 2 and 0. And notice what I'm adding up this time is I'm adding up cylinders. I'm not adding up rectangles. Well, I am actually adding up rectangles. I'm not going to belabor this point, but you know, if you cheat in your calculator and go over and type this mess in right here, it's going to find the area under the x to the fourth curve. But given that it came from this statement right here, the area that's under this curve is going to be the volume of this shape we rotated. So that's kind of interesting. And again, I'm very happy to have 0 here because when I put 0 in, I'm going to get nothing. So I end up with 2 to the 5th over 5, which is 32, minus 0 over 5. And so it's 32 pi over 5. And I guess I'll just leave it that way. But again, I kind of like writing, just for my own knowledge, as I said yesterday, I like writing cubic units or cubic inches or cubic something, just to kind of remind myself, hey, that's actually the volume of that, well, that roof that was on that house that I drew.
Hey, Doug, on the test, do you want exact answers or decimal answers?
Probably won't say, and I really don't care.
Sounds great.
As long as I see the work there. And also, if I create a problem on a test where the integral that you have here to take is really hard, I might just say set up the integral but don't solve it. Or I might say set up the integral and then cheat in Desmos or your graphing calculator to answer it. Because we already sort of practiced in chapter 5 taking integrals, and I don't want too much of this test to be that. But you know, this is an example of one where you should just go ahead and do it yourself.
Hey, Doug, can I insert a homework question real quick?
Absolutely.
So you don't have to open My Open Math, but in My Open Math, there's like multiple equations and you have to spin it around the x-axis. And I kind of looked it up in the book and stuff, and it says to subtract equations.
Yep.
But to solve that in Desmos, would you just subtract the equations, then plug it in, and then put it in Desmos?
Yeah, well, let's go ahead and do that right now. Let's modify this question and spin something a little different around the graph. And maybe we'll end up using Desmos. So let's go ahead and go there, and let's just make sure I make up a problem that's decent. So let's pick y equals x squared again, just to reuse a nice simple equation. And let's also go in and graph a line. Let's say y equals, I don't know, 2x, 3x. Let's try 3x and see if that comes out okay. Yeah, okay. So let's take the region that's bound by those two graphs and let's spin that around the x-axis. So we just did this, except for we went from 0 to 2. But let's take that region bound by those two curves and spin it around the x-axis and see what volume we get for that. And I'm gonna torque this out to try to make the drawing a little easier for us to see. So I just distorted the way it looks. I'm gonna cheat to get those intersection points. I think I got everything I need. And so let's just, and I was really not careful enough with this yesterday. I actually did some things. I actually got some answers embarrassingly full wrong yesterday. I fixed them in what I posted, but man, that's embarrassing. But we'll get it right now. Now, just to highlight this, What I just said a second ago, before we dive into this question, what I just said a second ago is you knew what I meant by it. And so everything went just fine. But realistically, we really took a region bound by y equals x squared and the line y equals 0 and the line x equals 2. In other words, y equals 0, the parabola, and x equals 2. Does it make sense? If we took that region right there and spun it around the x-axis, that creates a solid. Whereas technically what I just did a second ago, when I spun only the red parabola around the shape, does it make sense? That did not make a solid. It just made like an area, I guess, like a surface area. It was hollow, if you will. Does that make sense? Now that's a technicality, but you'll see in the book, they're going to be more careful about that. They're going to pick three things. So they'll say, consider the region bounded by y equals x squared and y equals 0 and x equals 2. And so then you draw three of those in and you're like, oh, okay, that region right there. Okay, now spin that around one of the axes and then find its volume. Because you're not going to get a volume if you don't spin an area. Does that make sense?
So Doug, we just found the area of that filled in though, right?
Yeah, so what I just said, you knew what I meant. We found the volume a second ago. It's not that our answer was wrong. It's 32 pi over 5. But my point was, if we spun a parabola around, we're not getting a volume. Do you see what I'm saying technically? So don't be confused by that. You knew I meant a volume because we said, let's just figure out the volume of that space that it fills. And, so we're thinking of it as a snow cone. Yeah, it's hollow, but I'm going to fill it up with stuff, right? So that's a little bit what Eve was just getting at. So in this case, it actually took both of these equations to define this space here. And now we're going to spin this around that axis. Now, just because I can, I'm going to show you something really quick here. So I'm always kind of talking about drawing stuff in AutoCAD. So watch, I hope I can remember how to do this because I'm not even sure I can, but so I'm going to draw a circle. AutoCAD is not really very good with parabolas. So I'm going to draw a shape kind of similar to what we're drawing right now. So there's an area right there kind of defined inside here. And I'm going to, just so we don't lose that, I'm going to copy it over here. And now I'm going to trim it all up, trim. So it's that shape that we're going to rotate. Now, right now, would you agree that's like two separate lines? And so if I remember right, I don't think I can actually rotate that and make it a solid. I think I have to join it together. So I'm going to use this command called polyline edit. Yes, J for join. So now when I click on those, do you see how they're acting as one? Man, I hope I remember how to do this. I should have practiced this ahead. Region. So now when I just clicked on it, I think I even filled the space inside it, if you will. So before it was like hollow. Do you see what I'm saying? And now I just made it a region. And so now I'm going to come down here and draw a line. This is not exactly what we're doing, but actually I think I'll do both. I'm going to copy it over here. So there's kind of the x-axis, and there's a command called revolve. And I'm going to revolve that region around this line. And I don't know if you can see down there, but it's saying angle of revolution, 360 degrees. Yes. Uh-oh. So if I shade this, do you see what we're talking about making here? Notice the inside of that is curved. And the outside, so it's like the outside is a cone, but the inside is curved. So the hard part about this is like picturing what it is you're trying to do. Now ours was touching, and for some reason this didn't work just a second ago, so I'll try it one more time. It's not letting me do that. I don't know why.
Hey Doug, are you good at Civil 3D?
Haven't played with it. No, what I'm using here is pretty old school, actually. Is that something you've played with?
No, I did a job shadow, and I think he recommended AutoCAD 2018 and then Civil 3D, something like that.
Yeah. So just because I can, I want to at least give you a little bit more of an understanding of what shape we're making right now. Do you understand that's the shape we're making? On the outside, it looks like a cone, but the inside it's hollow. So in a sense, I've got to find the volume of a cone, but then I got to subtract all that stuff off on the inside. That's kind of what we're trying to make. So some of this is hard because you have to have the ability to kind of picture what it is you're drawing. And so this is getting back to what Eve's question about subtraction then. So if I rotate that thing around the x-axis, the question is, do you see that the slices this time are not cylinders, but our slices actually look like this? I don't know if that makes sense to you. So I'm going to attempt to sketch this a little bit just to give you a chance to think about it. Let's see, I'm going to try to draw a mirror image of what I just drew, which is probably going to come out terrible. That came out way better than it should have. And that blue color looks pretty close. Straighten this out. So the question is, do you see these slices this time going from here to here? Except for they are hollow, meaning there's a center missing out of this as well. Do you see what I mean? They're not cylinders, they're cylinders with a hole missing out of it. It's like a cylinder minus a cylinder, which is where the subtraction business comes in.
It's like a donut.
Exactly. Your book, most calculus books will call this a washer.
That was the next thing I was actually about to say.
Because the donut's technically round.
Yeah, I was thinking about it. I was like, well, no, yeah.
So let's think about this a little bit. Would you agree that this distance up to here is kind of our larger radius, which is really the y coordinate of the line? Because that's how tall the radius is. It runs all the way up to hit the blue line. Whereas the green one is also y, but it's the y coordinate of the parabola. Does that make sense? And so this is very similar to what we just did a minute ago. If it was only the cone portion of this, which we'll redo in just a second, it would be, I guess I'll stick with the same colors because it might help a little bit. The cone would be the integral of pi r squared h. But for us, that'd be pi times the radius, which is the y coordinate of the line, squared times the height, which is in both cases dx. It's horizontal. It's a little bit of x. I guess I'll pull the pi out front. Would you agree that that would give us kind of the black cylinder, but not hollowed out? So that's no different than what we just did a second ago. Except for the line is our equation. Well, isn't the inner cylinder exactly the same? So that was kind of the blue cone, if you will. Well, let's take a look at the second one. The red curved cone, if you will. Isn't it exactly the same? Pi times radius squared times h. It's just that its radius is, well, we said the y of the parabola squared dx. That creates the green cylinder. So aren't I just subtracting those? Do you see the logic in that? I'm just subtracting those. You could do them separately. So you could say separately, the volume would equal pi times y of L squared dx minus pi times y of the parabola squared dx. You could do them separately, but couldn't we just do them together? Isn't that what we decided about derivatives and integrals? They don't mind plus signs. But what you can't do, my friends, is this. To make the point even more strongly, since all I have is a not equal, I'll do that. Why can't you do that?
Because they're squared when you subtract them.
Because
Maybe.
that's foiling them. They're not connected.
Yeah, I mean, you might be able, there's a number of ways to think about this. But one of them is if I foiled that out, I wouldn't get the same thing that I had above. But more importantly, just think about the picture up here. If I go y minus y, don't I get this distance right here? I'm going to erase that. Isn't that the distance I get if I go y minus y? Well, is that the radius of anything in this problem? Is that length the radius of something here? It's not the radius of something here. So it's tricky. Now, yesterday, when we did the weird questions where we said, hey, let's take that cool little curve there, let's fill it up with squares. Well, maybe that distance that I just drew in there, this distance right here, maybe that distance, maybe that distance is the size of a square. That makes that confusing. But for shapes that are rotated, and I'll tell you right now, I'm not going to give you any questions about volume that aren't just things being rotated. I think that's the more practical example. I don't think you see anything except for these kinds of rotational questions in the take-home quiz that I gave you that you owe me, I think Wednesday later in this week. Hopefully you're working on that. And you won't see anything on the test. So let's keep going. As I said before, do you notice that you get, well, dx's and y's? You get x's and y's. You're always going to get kind of a mixture of those things. And so what I'd really like to do then is, well, get rid of those. Like, you know, what is the y equation? Well, the y line equation, is just equal to 3x. And so I can replace YL with 3x. And so I can have x's. And the same thing is true up here. The y parabola equation is x squared. And so can't I replace those? So now I have all x's. And notice the line is outside or higher than the parabola. So it's got to be line minus parabola, not parabola minus line. So then I could say volume equals pi times y line, which was 3x squared minus y parabola, which is x squared squared. What's wrong with this statement right here that you don't want to do?
There
Yeah,
should be
there's squares.
parentheses around the 3x, between the 3x and the squared.
Yeah, the whole 3x is being squared. Now, if you're out of laziness, write it that way. And then your next step says 9x squared, fine. But the 3 is part of it, right? It's the y that's squared, and everything that's y is squared. And so you probably want to put parentheses there not to screw that up. And so now, cool, I'm in x land, if you will. Everything is x's, which means, okay, great. Then what are the limits of integration here? Well, what x's does this live between? I see that I barely caught the fact that this was a 3 up here. So they intersected up there at 3 and down here at 0. So all of this is happening while these washers slide their way from 0. Notice their washers are really tiny right down here when x is 0.1 and x is 0.2, but x has got to change. Do you see what I'm saying? We've got to march our way between x is 0 and x is 3 while the washers get taller and taller. What do the washers look like out here, by the way? Can you picture what those look like?
It's like circular noodles, basically.
Exactly. It's going to be really thin. You know what I'm saying? So it's going to look like a noodle that you wrapped around the corner because it's going to be huge hollow space. This one has a relatively small hollow space, but this one out here is going to be gigantically hollow, if you will. So that's why it's so important to come back here and say all of this is happening while x is everything, all the billion numbers that x could be between 0 and 3. And notice again, in this case, we're left with a really easy integral to take, because if I worry about the pi later, 3x squared is really 9x squared, and x squared squared is really x to the 4th. On a test, that would be an easy integral for me to ask you to take. It isn't going to take you much time. You're probably not going to get that integral wrong. So again, don't make me take points off for this. So I take the integral of x squared, it becomes cubed. I divide 9 by 3. Hey, that goes in evenly. So there's the integral of 9x squared. And x to the 4th, as we saw a minute ago, is x to the 5th over 5, or 1/5 x. But, you know, write it this way. The integral has been taken. So this right here is the first place I could cheat in my graphing calculator. But again, what's so weird about this is, what are you going to get? If you type this in your calculator, what's the calculator going to show you? What's Desmos going to show you? It's going to show you the area under this curve, the area, not a volume. It's going to show you the area under this curve between 3 and 0. And the answer to that area is actually the volume of this shape that we're talking about. So it's kind of amazing, if you will, that the answer to this is a volume. So part of me is kind of glad that I don't have to cheat, because if I went to a graph, I'd almost think, wait a second, what is that? I don't even understand what I'm finding here. Again, I'm very happy to go to 0, because when I put 0 in, nothing happens. And so I end up with pi times 3 cubed is 27 times 3 is 81. I'm going to keep going. 3 raised to the 5th equals. So I end up with 81 minus 48.6. So we end up with 32.4. And then when I put 0 in, I get 0. So the answer is 32.4 pi. Would you agree that's a weird way to answer it? I mean, it's perfect because I got lucky and the decimal that I got was a terminating decimal. So I can say equals here. But it's kind of funny to, give a decimal answer and pi in it. So, if a person wanted to say times pi, and because pi is an irrational number, you get 101.8. So, writing approximately 101.8. Again, cubic centimeters or cubic inches or something. I mean, isn't that crazy that you're finding the volume of that shape that I just drew in AutoCAD? I mean, a shape that nobody can do, but like these kind of shapes get made all the time now by people in machine shops. And so the fact that you could make a shape like that or find its volume is really kind of cool. My point is nobody in the real world wants 32.4 pi for an answer. My open math might, but they would want 102 cubic centimeters or whatever.
So in machine shops, are they putting these calculations into a machine, or is it kind of just like AutoCAD where you're just drawing the shape that you want?
Yeah, in the world that we live in, people usually draw it in AutoCAD and let's see, am I going to share this? Because of that solid shape that I just made it ago, because I made it in a computer program, I can actually click on it and ask it its volume, and that's why that program costs so much money, because it'll just tell you what it is. In my case, it won't match this. That's why I'm not going to go over there, because I didn't draw a parabola. Does that make sense? I just drew something conceptual to help you understand what you're looking at.
Yeah, that makes sense.
Anybody know how to cheat? If you have something super weird and you want to know its volume, what's the way to cheat that's actually really cool? Even something crazy, like if I wanted to know the volume of this mouse, does it make sense? As cool as what I'm showing you is, it's very hard to describe this mouse in the way that something is rotated in 3 dimensions, if you will. Like that's not going to happen. But how could I find the volume of this mouse really without knowing hardly anything?
Could you just weigh it?
Yes, if you know the density. If you know the density of the material it's weighed, or that it's made of, if it's all made of brass, then you could weigh it and use the density to get its volume. That's exactly right. Even easier, put it in water. If you have a beaker with water and it's up to say 50 milliliters, and you drop your object in and it goes up to 60 milliliters, then you go, oh, it's 10. Doesn't matter how weird the shape is.
So what would the units? It would be 10 milliliters cubed.
Yes, no, 10 milliliters. But if I remember right, a milliliter is a cubic centimeter. So in metric, is that right? Maybe somebody remembers milliliter. I can't remember what the conversion is. Or is it 1,000 milliliters is 1 cubic centimeter or something like that? I forgot what the conversion is,
but there is a conversion.
Yeah, there's a conversion. Mm-hmm. So I wonder what would happen if we tried to spin that around the y-axis, the same exact shape. I wonder what would happen if we spun it around the y-axis. So I'm going to redraw that for you, and this time give you a little bit of time to see if you can set up the integral yourself. And I'll give you a clean drawing of it. Without chopping off the So try to set that up. Try to write it down wrong.
Would it not be the same shape, just like in a different position though?
That's a great question. Like, is it the same shape? I think I am gonna stop sharing for a second and give you a chance to visualize this over here in AutoCAD, because this will help us.
You know, I don't think it is the same shape because the part that made the hollowed out center before is now on the outside. So doesn't that like switch the shape?
Say that again, Eve, and everybody think about what you just said.
So because we're kind of flipping it, so now, sorry, my alarm's going off.
Time to wake up.
So now we have the outside, like the parabola is now on the outside and the straight line's on the inside, or not the straight line, but the curved line is on the inside. Doesn't that switch which one's hollowing out the center?
Do you think she's right? Like down here, because the line was on the outside was the cone and the inside was curved. What Eve is saying is if we took this region up here, and I'm going to purposely, there we go. I'm going to purposely miss that by a little bit. If I spin it around, revolve, notice the command revolve. If I revolve this region around this object.
I don't think we can see your screen.
Yeah, you're not sharing your screen.
Thank you. User error. I'm gonna undo that. So you can watch it happen again. So here's the region this time, but this time we're gonna spin it around the y-axis. So if I say REV for revolve, I select that object, and then it asks me, what do you want to revolve it around? And I drew a line here. Notice I drew it purposely a little further apart, a little off that a little bit. So I say this object is Eve correct? That it's not the same shape?
Yeah, that makes sense.
Yeah, she is correct, because the outer part is not a cone now, it's curved, and the inner part is a cone. Does that make sense? So it's curved on the outside, cone shaped on the inside now. So no, this is not the same shape. So it's not going to have the same answer. You may also be able to tell the shape is further away from the, maybe I can't tell that. I can't tell that because I distorted the screen. But the important thing here is if I just went up to some random point, isn't that the x coordinate of the parabola? Whereas this distance is the x coordinate of the line. Need to do this with a different color. So the question is, do you see this as the exact reverse of what we just did a minute ago? In other words, the purple is pi times its radius squared times height, but that radius for the purple one is the parabola. So that's like the x coordinate of the parabola. And this time, because its height is vertical, isn't it dy? So this is like the outer cylinder minus the inner cylinder. Which is the same exact equation, pi times radius squared times h. But the inner one, the radius is the x of the line, and the height is still dx. So I could put them all together and just have 1 pi, change colors. And I'd have x p squared dy minus xl squared dx. Oops, sorry, that's dy as well. Last time it was y's squared and then dx. This time it's x squared and dy. So my advice to you was to say you're stuck with y because of dy. So it'd be easier to replace those x's. Well, again, don't I have a way to do that back up here? Doesn't this imply that x for the parabola would be equal to the square root of y if I just resolve that one? And this one implies that x for the line would be equal to y over 3. So I have x for the parabola, which is the square root of y, and it is squared. And I have x for the line, which is y over 3, and it is squared. And by the way, you don't really need both of these dy's. You could just have one of them. And now that I'm working with y's, does it make sense I need to go back to the picture and say, okay, well, for what y's does this cool shape that I'm spinning exist? And I see, I'm looking at y, and so that happens from y is 9 to y is 0. So fortunately, the square root of y squared is y, and y squared over 3 would actually be y squared over 9. And again, we sort of got lucky. That's not a terribly hard integral to take, so there's no reason we shouldn't just go ahead and take it, I think. I think I can fit this in this page, so I might as well scoot it over and do it. So again, to speak correctly, I'm going to take the integral, so it is now taken. So I'd have y squared over 2, or 1/2 y squared because of the power rule. Y cubed over 3, 3 times 9 is 27. So I'd have 1/27 y cubed, and I just need to evaluate that at 9 and at 0. And just like last time, again, having 0 involved is great because 0 is going to be 0. So that's awesome. So 1/2 times 9 squared minus 9 to the third divided by 27. Maybe we'll luck out and that'll be a whole number. It isn't a whole number, but it's darn close. I got 13.5 when I stuck 9 in. I got 0 when I stuck 0 in, and so I got 13.5 pi, which is approximately 42.4. I got a decimal that went on forever. Again, cubic inches or cubic centimeters. Maybe I'll write inches this time. I don't care on a test just because the graph paper has no units. If you just give me an answer, I'm not going to mark it wrong, but it's just kind of cool to know that that's a volume, or, at least say volume equals 13.5 pi or something like that.
Can I interject real quick?
Please.
So when doing the assignment last night, it actually didn't use this method, and instead it used something called the shell method.
Yeah, which is tomorrow's discussion. Do you notice that this worked great because we were able to switch to another, like I was able to re-solve that for X pretty easily. But if that equation, I'm going to erase this, had been y equals x squared plus 2x, does it make sense? It would have been hard to find out how to solve that for x. Does that make sense? That would have been very hard to do. So there's a method called, there's another way to look at this that we'll talk about tomorrow and the next day that allows you to not have to do that. So if I just slightly messed with that parabola, that would have made this problem really hard. So we'll get there. Was that in the 6.3 or 6.4 assignment?
6.3.
No, that's not good. So if there's a question that talks about shells or cylindrical shells, we're going to talk about that tomorrow. Don't want to overwhelm you in one day. Let's see. So I'm not a person for, I think it's much better to draw pictures and reason this stuff out for yourself, because all we really had to have here is a decent picture in our mind, or even a physical picture, ideally. And we just had to know the volume of a cylinder. But just notice a couple of things we noticed a second ago. So notice if you're going around the x-axis, then the equation was, let's see, because we went around the x-axis, it was y's that were squared dx. In other words, you ended up with pi times y squared dx. Since your cylinders have a y coordinate for a radius, right? If you're going around the y-axis, your radius is a y value, and then your thickness is a dx, which I notice I just wrote wrong. It's a dx. Your thickness is a dx. Does that make sense? Whereas if you go around the y-axis, it ends up pi times x squared dy. That's because if you go around the x-axis, then your cylinders look like this, which means their height is y and their radius would be x. So it's the radius squared times the height. So see how they're backwards? Like they're always going to be a mixture of x's and y's. Now, if I'm you and I'm just learning this, like that might be a good thing for me to just kind of stare at. But if you draw the picture, I don't think you don't need to memorize that or write that down or whatever. And then I guess I could add, if the shape is hollow as it was for us, then it really ends up pi times y1 squared minus y2 squared dx. You understand what I mean by that? There's just two of them. Like, there's just two of them. You got an inner and an outer radius. So if this had a hollow hole in the middle of it, then, you know, that'd be like y2, and this is y1. So you have the bigger radius minus the littler radius. So there's just a second set of them, that's all. This one down here is hollow, same thing happens. You end up with x1, the x coordinate of the outer one minus the x coordinate of the inner one. And maybe that'd even be a better way to say it, like outer and inner. Does that make sense? So let me show you something cool. Again, just to help you make sense of this. You may remember the formula for the volume of a cone. You've been given this for years in algebra classes, and it's like, and I don't know if you've had any occasion to ever think about this, but that 1/3, do you understand what that 1/3 is telling you? Like, isn't that the same formula? Like pi r squared h, isn't that the volume of a cylinder? So if you come back and say, I'd like to know the volume of a cone, what you're being told here is that the cone's volume is exactly 1/3 of the cylinder it would fit inside. Does that make sense? And you could kind of perform that with rice, if you will. If you had think of a snow cone, because a snow cone is hollow. If you filled it with rice and you had a cylinder that was the same height, you could dump 3 snow cones full of rice into it and it would fill it up to the top exactly. So where does the 1/3 come from? Well, let's make it like that formula we've been given all the time you've been shown this. Nobody ever showed you where that came from. They just said, this is what it is. And then you got an answer and they told you it was right. But let's see if we can actually make it. Let's make this formula. Not prove it, make it. Make it for yourself. Like you're about to be able to own this formula. So watch how I'm going to use this logic to do it. So what I'm going to do is take this line right here with a radius of r and a height of h, and I'm going to spin it around the x-axis. Can you appreciate that's going to make a cone? So let's picture our little cylinders we're going to add up. Aren't they going to look like this? Notice this isn't hollow this time. This is not a washer. There's no hole, thank God. It's not two shapes that are away from one of the x or the y axis. It's solid. Good deal. I only need one of these. And this is kind of my basic equation right here. It's not hollow. Now, if it wasn't for algebra, I would just kind of be stuck with this statement. And by the way, notice R is that distance right there. Back inside the shape, as I slide this cylinder this way and this way, that's not, the radius of that is not staying R. Does that make sense? Does it make sense to you that that radius is really Y? Because it's varying. Down here, Y is going to be really short. Over where I drew it, pretty long. At the very bottom, it's going to be the full radius of the cone. And isn't this little thickness going to be dx? And so again, just like always, our stack of cylinders, our sum of cylinders is going to be pi times radius squared times height. But how are we going to get rid of y? Who can tell us? Well, what's more challenging about this question is there's no equations here. You got to make them yourself. So the question is, can you make that equation right there yourself? What's the equation of that relates x and y? You should be able to make its equation. Do you know what the slope of that line is? You know it's a line, right? What's the slope of that line?
Y minus y over x minus x.
That's exactly right. Slope is y minus y over x minus x. But in this picture, it's even easier than that, because to get from here to here, don't you rise r and run h? So isn't the slope just r over h? Now to Eve's point, this is the point 0, 0, and wouldn't this be the point over h up r? So this is the point hr. So if you go y minus y, r minus 0 over h minus 0, don't you get r over h? The slope of that is r over h. So that means this equation is y equals slope of r over h times x plus what else goes with that line? Is it plus 2, plus 6, minus 7? What's the... Come on, algebra people.
It's 0 since the y-intercept is at 0.
Good job. I purposely asked you as though there should be something there, but it crosses at 0. So isn't it, it's y-intercept 0? And notice if you put 0, 0 into that equation, it works. But even if you put h, if you put h in for x and you put r in for y, notice it also works because the h's cancel and you get r equals r. So you could plug points in. Well, you had to make the equation yourself, but there's the equation that connects those two statements. So that means y is equal to r over hx, which means I can switch that out. So I say, okay, great. Well, then this is r over h times x. It's still being squared. What are my limits of integration? Where does this cone live in terms of x? What are its values?
0 to h.
Yeah, 0 to h. Good job. So you try it. Can you take that integral? Now you're going to get a formula this time. And just note to yourself that you're going to treat r and h as constants. So the integral of r is not r squared. R is like 7. So you're treating those as a constant. So that's really kind of like the integral of 5x squared or 9x squared or something like that. Just going to give you a second to try that on your own. Notice the R and the H are also squared. So I just squared that, and now I realize, oh, that's an easy integral to take again, as long as you recognize that R and H are constants. Well, hey, if they're constants, couldn't I just put them out front? And like ignore them so I don't screw up? Sure, if you want to. You can leave them in there, doesn't matter. But they're constants. Now I'm going to take the integral. Now do you see perhaps for the first time why there's a 1/3? There's a 1/3 because the integral of something squared grows to a 3, and then you divide by 3. That 3 that just materialized on the bottom of that fraction is where the 1/3 came from in that formula. Now I evaluate this at H and it's 0. Fortunately, when I evaluate it at 0, nothing happens. But just to go slow, if I evaluate that at H, I get H cubed over 3. If I evaluate it at 0, I get 0 over 3. So you end up with pi r squared H cubed over 3H squared. Hey, that's the formula for the volume of a cone. The H cubed cancels with the H squared, and you get pi r squared H over 3. Most of the volume equations that we have were indebted to calculus 4. There's a number of them, crazy ones. Let's see. I'm going to show you something here really quick. I doubt any of you know, like a lot of these geometry formulas, you know, like, hey, look, and I'm only looking at volume here. Look, volume, length times width times height. I know that. And maybe, you know the cylinder one that we've been using today. Most of you probably don't know the pyramid one. You probably know the cone one, but I bet none of you know that one. It's called technically a frustum of a cone, but it's really like a truncated cone. The top is chopped off. Notice it's 1/3 pi h times r capital R squared, which is like the radius of the bottom of that cone. But then there's also a little r, which is like the shorter radius. Now, the reason this is particularly interesting to me is because that shape is so ubiquitous. In other words, everywhere, because that's a coffee cup. That's the coffee cup that you buy Dutch Brothers that's shaped like that. So it's a shape that we are interacting with the volume of this constantly. And so we say, they say, what size do you want? And you say usually 12 or 16 ounces or something. And, it's only coffee, so you don't really care. But somebody had to be the one that calculated that. Somebody had to be the one to make a 16-ounce cup. Could you do that? So what I want to offer you for extra credit is, could you build this formula just like I built the simpler one? Could you draw, and I'll start this for you in a second. So if you want to attempt this, write that down. By the way, notice down here is a sphere. We have a formula for that, 4/3 pi r cubed. I wonder why there's a cubed and a 3 down there. I wonder if the integral of something squared would grew that 3 and then you divide by 3. I wonder if that's why that 3 is down there. So we got some things to think about. Most of what calculus does for us actually is create, and this is true of a lot of things, but it creates algebra formulas, and then we don't really need calculus anymore. In other words, you've been using calculus your whole life. that somebody else did for you, just didn't know it. So do we need calculus? Well, one argument is no. We had some smart person that made these formulas, and these are the formulas I need to, design coffee cups and build buildings and so forth. And now we have these algebra formulas, and so I don't need calculus for that. Turns out in the engineering I teach, there's a whole bunch of really cool formulas that we use in engineering that calculus created the formula. And so, we have this little shortcut algebra formula, but it was calculus that invented it for us. So let me show you kind of what that might look like if you were to tackle that extra credit problem. And I would highly recommend you do this, just because it's such a powerful feeling of control, that you can actually make these things for yourself. They're like tools that you can make for yourself, not just something you have to look up and Google search. So let's see, what would that look like? I'm just redrawing what we just did a second ago. Except for now, we sort of have little radius and we have big radius. And we have this height right here. And so I think you want to aim this just to make, because again, you're going to need the equation of this line here. The question is, could you build that formula for the volume of that shape? Ultimately, you're trying to find, I'm even going to turn it upside down so it looks like a coffee cup. So we saw, if I remember right, 1/3 pi r, no, it wasn't pi r squared. It was 1/3 pi h, wasn't it? H times r squared. Was it plus capital R little r plus little r squared? Is that what it was?
Yeah.
Thank you. Can you build this by, again, considering this to be rotated around the x-axis? So for your homework assignment questions, they're going to say something like, consider the region bound by the line y equals 1/2 x, the line y equals 1/2 x, the line x equals 7, x equals 2, and the line y equals 0. Like, it took 4 equations to define this region. So now we have this green space. So it's an area, and now we're going to spin it. Okay, well, if you spin that, you have a volume. Does that make sense? So that's why they're not just going to say, hey, just take this line right here and spin it, because if you do, it's hollow. So it's kind of a technicality. So let's see. Yeah, it's 9:20. I was tempted to start. I'm going to write this down, but I'm not going to do it, but I want to write it down. I wonder if you could conceptualize, how can you think of a sphere in the language that we've been describing right now? What could I rotate? What would I be rotating around something to make that happen? Blurt it out so we don't run out of time.
A
Circles.
circle?
Yeah. Circle. So I'm thinking if I took that circle right there, and just to keep it simple, and that equation is x squared plus y squared equals r squared. But of course, the circle would keep going all the way around here, right? but I'm just going to consider that quarter of it. And to keep it simple, I'm just going to send it around the x-axis again because I'm feeling comfortable with that. But if I took just this space right here and spun it around, does it make sense that would give me a half sphere? And then I could double it. Like, does it make sense this is where that formula came from? Now, the difficulty in this problem is the fact that when you solve this for y, you get r squared minus x squared. Actually, I'm not sure this is difficult. Now, let's go ahead and do it really quick. This isn't going to take long. If you need to leave, leave, but this will only just take a second. I'm suddenly realizing this isn't going to be a hard problem. So wouldn't the, as all of these problems, wouldn't this be the integral of pi times the radius squared times the height of our cylinder? And in our case, we need to double this. So that 2 is coming from this side over here. So that'd be 2 times the, I'll take pi outside 2, times the radius. But what's our radius? What are these radiuses? Well, aren't those y values? And isn't our thickness, as it was in all of these problems, a little bit of x? At first I was thinking this was going to be really hard and that's why I wasn't going to do it. But why is it not going to be hard when I substitute y in place of y here? Why is that not going to be hard?
That square root's going to cancel.
Square root's going to cancel. If that square root doesn't cancel, this is nasty. So we got 2 pi, I'll go fast. And then I just have r squared minus x squared dx, don't I? And what's the limits of integration for this? What r values, I'm sorry, what y values, no, x values, what x values, where does this go? Where does our little cylinder slide to? Everywhere from, well, here to here. What values does it slide to?
Is it 0 to pi?
Close.
0 to 2 pi.
Isn't this distance right here r? In other words, that's a circle of radius r. So that means this is the point r0 out here. In other words, that's r. So it's going to be everything from r to 0. You see that now? Remember, r is a constant. So r is a constant is a pretty important idea here. Well, if that's true, then don't we have 2 times pi? So then the integral of r squared, because r squared is like 9, isn't the integral of 9 9x? So the integral of r squared is r squared x. But x isn't a constant. The integral of x squared is 1/3 x cubed. So I need to evaluate that at r and evaluate that at 0. So when I put r inside that, when that r goes here, I have r squared times r, which is r cubed. And when I put r in here for x, I have r cubed times 1/3. And then when I put 0 in, I have just a bunch of zeros. Hey, look at that. 1/3 r cubed plus r cubed is 4/3 r cubed. Except for that didn't come out right. Why not? Because when I multiply that by 2, don't I get 8/3 pi r cubed? Which is not true. Anybody see why? I don't. Oh, stupid mistake. What stupid mistake did I make? What do you notice?
Did
right
you
here?
add a cubed
No,
from your r squared to r cubed?
Did you forget the square root?
no, everything's fine. But what do you notice right here? That's a minus sign. What happened down below? Turned it to a plus sign. What's r cubed minus 1/3 r cubed?
2/3.
2/3, and then you double it and it turns into 4/3. So you've used this formula your whole life, but it was calculus that gave us to us. Does that make sense? This is powerful stuff. Okay, if you didn't already get out of here since I'm late, as Eve said, why don't we just say this class goes from 8 to 9:30 because that's what always happens. Stay after if you want. Dig further into the homework questions. We'll talk about a cool method tomorrow, but fortunately we're going to spend 2 more days on the same logic, the same thinking, because this is a lot to get your mind around.
Hey Doug, I just wanted to pick up on yesterday and confirm that 2A on the quiz was 1.6 million.
Thank you for reminding me of that. I'm looking right now. Yep.
Very cool. Thank you.
Will you be in your office hour today?
Yes, I will make a note to be so.
Okay, because I got your email about that integral, so I'm gonna try my hand at that and then probably pop in there and give you my results.
Yeah, sounds good. And it's actually, that's tricky. I don't know if I said enough to point you in the right direction, but the sine of 2x is equal to 2 times sine of x cosine of x. And so that's what you have. You have the sine of 2 times junk. So that's your way out of that mess, which is surprising, but it does indeed work. Yeah, let's finish that today. I'll set an alarm for 12:30. I teach from 11 to 12:30, and it's technically 11:20, but that class is always kind of goes till 12:30. So I'll pop in there as soon as I get out of that class.
Yeah, and I can show up later if that works better for you.
No, it should be fine. I mean,
Okay.
just go
I'll
in
see
there
you
and
then.
start working on it, and then I'll pop in as soon as I can. I'm setting an alarm right now just to make sure I actually do it. So,
Okay, thank you.
yep.